Hey everyone, my name is Leto Yoshi. Today I wanna talk to you about the voltage drop. So what is voltage drop and why it is important? So put on your thinking cap and let's get started. So voltage drop is one of the most common failure of the electrical circuit. It is can be thought of as a wasted electricity. It is simply the difference between the voltage measurement at the source and the point of use. Besides painful electricity you don't receive, voltage drop can cause us a problem as well. If you have too much voltage drop in the circuit, it can damage an equipment you are trying to operate. Like in the motor circuit, actually burn up the motor, or in the branch circuit or feeder wiring, it can cause extensive damage to the wiring. But it's not possible to have a zero voltage drop because some voltage loss is going to occur naturally from the impedance of conductors themselves. There are no material with zero impedance, even if great conductor like copper or aluminum, as far as I know. So no matter how short length wire, no matter how wide diameter, there are still few impedance exist. So the goal of this topic is to minimize the voltage drop as much as possible. Of course, after considering some practical factors like designing factors like material cost or construction labor or something like that. Okay, so let's think about how does a voltage drop occur by this power system formed by AC source, like secondary or power transformer or a simplified version of a generator, and they are feeding the load like so. And joining source to the load, there is a cable or feeder represented by resistance and reactance associated with inductance of that cable. A source voltage given as a Vs. Of course, it's a phasor. Similarly, at the load, we have a VL voltage on the load. As soon as we apply the voltage to the load, there is a current I, another phasor flowing through the circuit, and this current will produce here the voltage drop VR and reactive part of the cable voltage drop Vx. VR is R times I from Ohm's law. That means VR is parallel the phasor I, and Bx is computed as a Jxi, and J is 90 degrees. That means Bx is perpendicular to the phasor of the current. Right? So let's think about Kirchhoff's voltage law at this growth path as absolute power at first. Or KPL, in the closed parts Bs, here absolute power equal BR plus Bx and V. And this can be thought of as a constant where it will never change, so the value of the BL is totally depending upon the values of voltage drop, meaning BR and Bx. So the higher the voltage drop, the lower the voltage on the load, and lower the voltage drop, the higher the voltage on the load. that is a voltage drop, and that is why we are trying to reduce as much as possible. But this is absolute value, it's not enough, so we need to think about that as a phasor problem. And if we choose as we usually do in a phasor problem, we need to select the reference, 0 degrees phase, and that is arbitrary if we are not given any phasor. Well, in this case, I will choose BL as my phasor reference phasor, like so. BL at 0 degrees, and there is a current I as a phasor, like so, and this is angle theta. What it tells us that the current is lagging behind the voltage by this angle theta, and the cosine of the theta is the power factor of this load, so this load is slightly inductive, like induction motors. And how about BR? BR is going to in phase with current, so BR is drawn like parallel to the phasor I, like so. BR. How about BX? BX is a perpendicular, so it's drawn like this is 90 degree BX. And if we add BR and BX like so, what is this voltage? Alright, so okay, BR and BX. So from this point to this point, that is a voltage on the cable. Alright? Okay. And how about this? Voltage on the load and the voltage on the cable add together, like so. What we get? Alright, BL and voltage on the load cable, so that is the voltage on the source BS. Okay. So how exactly calculate voltage drop from this equation? Alright, so let's go down step by step. So here, how about this angle? Of course, it's a theta. It's a parallel base. And how about this angle? That is also theta. So think about this two triangle here, and this is the same angle, and this is a 90 degree, so this is also theta. Drawing this line helps us easier to understand. So let's say how about this length here? How about this? This is BR times cosine theta. Okay, and how about this length here? This is the same as this length here, and this is Px sine theta. So this length here, Px times sine theta, alright? So how about here, this length? So this is the same as this length. This is a BR times sine theta, so BR times sine theta. And similarly, this length is the x times cosine theta. So here this length is, of course, it's the x times cosine theta minus dr times sine theta. Okay, so think about this triangle here. Okay, let me pick up this triangle, and how about this? Thanks, BL plus BR sine theta plus BX times sine theta. How about here? It's the same as this value, BX times cosine theta minus BR times sine theta. Right, so okay. And think about the Pythagorean theorem. I mean, in the triangle. So the relationship with this stuff is a square is going to equal b square plus c square. Alright. Okay. Let's say in this a triangle. Okay. PS square equal BL plus BR sine theta times plus BX times sine theta square plus BX times sine theta minus BR times sine theta square. Okay, so okay, let's say this number 3 term, third term is much smaller than this second term. I mean, this is minus and square, so we can omit this third term, like so. But if you want to calculate more accurate way, you can just use this formula at the original formula to remaining this term. That's okay, it's up to you. And okay, but think about the simple version here. Except this square is disappear, so this relation is BS equal BL cross alright. And so what is voltage drop? Just I mentioned, the voltage drop is the difference between the voltage source and point of views. This is a voltage source and this is point of view, so voltage drop let's say voltage drop BD equal BS minus BL, which is load, and that is here, and the BR and the BX is here respectively, so I times R cosine theta plus X sine theta. This is a formula the voltage drop calculation. In a practical calculation, there are some factors that we need to consider for this equation. The equation VD voltage drop equal some factors times cosine theta plus x sine theta. Okay, some factors as coefficients. The first one is whether the circuit is single phase or three phase. And in the single phase circuit, there are two. We need to multiply two this formula. Like so. Because there are two impedances, like here, 1 and 2, that is going and returning respectively. So we need to multiply 2 as coefficients. And on the other hand, the three-phase circuit, we need to multiply the square root 3. Right, so. And here also there's the impedance 1 and 2 and 3 points. So, but we need to careful about the difference, the value of the voltage. I mean, types of the voltage. So here this is line voltage, V line. But here this is phase voltage, V phase. And of course line voltage is equivalent to square root 3 phase voltage, and we need to consider pick up this single phase circuit. This is just the simple circuit, and there are no impedance because there are no current in the three-phase circuit. So, and this simple circuit is times 3. This is a total voltage drop on the three-phase circuit. So this is V phase, so we need to calculate as a phase voltage. So V phase is V line divided with square root 3, so 3i over square root 3, that means square root 3 times I as coefficients. So that is why this is a square root 3, not just 3. Okay, so let's calculate the practical some example of the voltage drop. Okay, here let's calculate this power system, the actual voltage drop. Okay, so this is the induction motor and the feeder, and this is cable, and 100 meter and this is the type of the cable. I think it's a Japanese style, and a number of the cable is 3 and 38 square millimeters, and the rated voltage is 200 volt and 50 hertz frequency, and the induction motor is rated current is 40 ampere and power factor is 0.85. So okay, let's do that. So you can refer to some code or standard according to your country's manufacturer, the cable manufacturer. Their constant values of the resistance and the reactance, depending upon the types of cable and diameter and length. Our resistance is 0.626 ohm per kilometer, right? Not just ohm per kilometer. And reactance is 0.0955 ohm per kilometer. So, okay, how about the total impedance is, of course, our sine theta plus x sine theta. This is, okay, just calculate 0.582 ohm per kilometer. Okay. Oh, by the way, sine theta is calculate here 0.526. So how about the voltage drop? Okay, voltage drop is calculated like voltage drop is some factors times current times length of cable times the impedance, right? And this is 3-phase power system, so square root 3 times 40 ampere times 0.1 kilometer 100 meter times 0.582 per kilometer. And this factor sometimes consider about temperature or number of conductor or some factors sometimes needed to consider, but it's just calculate a simple way. Just think about the types of the circuit. I mean, 3-phase circuit. So please refer to some code or standard according to your country or area. This is 4.0 volt. So the ratio of the respectively to the source voltage is 200 volt. volt is almost 2% voltage drop. I think it's not so much. And if we look at some international electrical code, it is recommended that the voltage drop should be less than 5% under the fully loaded condition. So 2% is okay, it's fine, I think. Well, thank you so much for watching my video. See you in the next time.